Hello, welcome back. We're going to take another example dealing with capacitance, charge, and potential difference across the plates, and we're going to see how these things change in various situations. So here's the question we're going to work with now. It says that a parallel plate capacitor with air between the plates, and remember air has a dielectric constant kappa of 1.0, has a capacitance of 4.0 microfarads. And it's asking us what the charges on the plates are when it's fully charged by a 6-volt battery. And then we insert Teflon between the plates, and it's asking for the capacitance, charge on the plates, and potential difference between the plates immediately after the Teflon is inserted and after a few minutes when the battery has fully charged the capacitor again. And as before, I've listed the equations and constants over here, but let's start with a picture. So I've got a capacitor that's got a capacitance of 1.0 because it's got air between the plates, and it's connected to a 6-volt battery. The way I've drawn it, the positive end of the battery is at the top, the negative end is at the bottom. And we're also given the capacitance of this capacitor. That's given to us as 4.0 microfarad. And after this battery has fully charged this capacitor, charges would be separated such that this plate would have a net positive charge and the bottom plate would have an equal net negative charge. So this plate will end up with a charge of plus Q at the end, and the bottom plate would end up with a charge of minus Q, and we're being asked for what this Q is. That's our first question. And because the battery has fully charged the capacitor, the delta VC here across the capacitor would become equal to the potential difference across the battery, so that would be 6.0 volts. As before, we can use this relationship between capacitance, charge, and potential difference to figure out this charge. So we had C equals Q over delta VC, which can be rearranged to give Q equals C times delta VC, and that simply becomes 4.0 times 10 to the negative 6 farad times 6 volts, and that gives us a charge of 24 microcoulomb. So that's the answer to the first question. And now we have changed the situation. We've still got the battery connected, but we're inserting a Teflon slab to fill the gap between the plates. So now I've got this kappa, let's call it kappa 2, becomes 2.0 because that's given as the dielectric constant of Teflon. So for comparison, let me change the old one to kappa 1. So now I got Teflon over here with this kappa, and it's asking us for two situations. Immediately after the Teflon slab is inserted, it's asking for what the capacitance, charge, and potential difference would be. And then it's asking for the same thing after the battery is given enough time to fully charge the capacitor. Okay, so let's do this A part over here, which is immediately after Teflon is inserted. So by saying immediately after the Teflon is inserted, we're basically saying that the battery hasn't had a chance to do whatever it needs to do based on the changed capacitance. We know that capacitance changes because we have now changed this dielectric constant. So we have changed how the capacitor is built, so we will have a new capacitance. But there's not any time for charges to move. So that's what tells us that Q here is 24 microcoulomb, the same value as it was before. So I've got plus 24 microcoulomb on the top plate, which is positively charged based on the battery's orientation, and minus 24 microcoulomb on the bottom plate. So what would be the capacitance in this case? As we showed you before, C2 over C1 equals kappa 2 over kappa 1. That's what we get when we use this equation for capacitance, and knowing that area or distance between the plates or epsilon did not change, the dependence on just kappa would be given by this equation. And in our case, kappa 2 over kappa 1 is 2.0 over 1.0, so that's simply 2. So this gives me C2 equals 2 times C1, and C1 back here was 4.0 microfarads, so this simply becomes 8.0 microfarad. So I know charge, I know capacitance, I can figure out the third variable using the second relationship. So delta VC, by rearranging that equation, would be equal to Q over C, and so this will be 24 microcoulomb over 8 microfarad. The micro is 10 to the negative 6, so those will cancel. So this will give me simply 3.0 volts. So let's pause here and take a look at this. This delta VC is now 3 volts. So we started with delta VC 0 between the two plates when they were just neutral. We connected it to a 6-volt battery and gave the battery enough time to charge the capacitor fully, and that meant that the potential difference across the plates of the capacitor is equal to the potential difference across the battery. That's what it means to get it fully charged, to attain equilibrium. Then we just inserted Teflon. So when we put the Teflon in, it changed the capacitance from 4 microfarad to 8 microfarad, which immediately dropped the potential difference between the plates to 3 volts because there was not enough time for any charges to move. So now, if we give it a little bit of time, this battery is now going to start working again. Things are no longer in equilibrium. I've got a 6-volt potential difference across the battery. I've got only a 3-volt potential difference across the plates of the capacitor. So the battery will begin working again and move charges until the potential difference across the plates of the capacitor once again becomes equal to the battery's potential difference of 6 volts. So for part B here, if we allow the battery to fully charge the capacitor again, this delta VC in this case across the capacitor will become equal to the potential difference across the battery, which is 6.0 volts. So by waiting for the battery to fully charge the capacitor, we haven't changed anything with the capacitor. The dielectric in between is still Teflon, so 2.0. The area of the plates did not change. The distance between the plates did not change. So the capacitance in this case is still what it was after the Teflon was inserted, so 8.0 microfarad. The potential difference between the plates of the capacitor does change to equal the battery's potential difference. That's when equilibrium is reached. So that'll be 6.0 volts. And so now we can figure out what the charge is. The charge would be C times delta VC. So that is 8.0 microfarad times 6.0 volt. And that'll give me 48 microcoulomb. So this tells me that the charge on the top plate here would grow to plus 48 microcoulomb from 24 microcoulomb that it was, and on the negative plate the charge will grow to minus 48 microcoulomb. So to just recap what happens between steps A and B over here, after the Teflon was inserted, because the potential difference between the plates dropped, the battery will start working again and it'll move more charge to re-establish the potential difference as 6 volts, and that will end up doubling the charge separation between these plates. In this slice of physics, we got some more practice working with capacitance, charge separation, and potential difference. And the important facts we used in this case was once again reminding ourselves that capacitance depends only on kappa, area of the plate, and distance between the plate, and that tells us when capacitance does and does not change and how it changes. And secondly, we saw in practice here what happens when the capacitance changes and the battery is not given enough time to move any charges. In that case, the charge separation remains fixed and the potential difference changes. And once we give enough time to the battery to do its thing, it'll move whatever charges it needs to move to make the potential difference across the plates of the capacitor equal to its own potential difference, and that results in a different level of charge separation than we had before. Thanks for watching. I'll see you later.